we were saying that if number of
This
atoms
call is
are
now being recorded.
if number of atoms are like 1220, okay, yeah, that is
Yes.
like this electronic magic number is dominating, and if it is 1415, so that
Yes.
structural,
Yes.
yeah. So, so that like till what kind of like number of atom it will be specified that it is a small particle or it is the large particle, like below 1220 atom we can say that electronic magic number is deciding that cluster size, and above 1415 we can say that structural one is deciding the cluster size.
Yes, I mean this is again it is not like a hard and fast rule that it should be like exactly this number. If it's like if this is a number and then this electronic magic number is the dominating factor, or the structural magic number will be the dominating factor. So it is again a very uh, really specific to probably specific to the material, like which kind of atoms you are using, whether you are using a single atom or you are taking an alloy, or uh, like a molecular complex, or if you have more than one atom. Okay, so all these things will decide this number. So what here we have mentioned this 1220 or 1415 is like typically for this is, let's say, one of the examples we saw this sodium. Okay, so in that case this is quite true. Let's say many of the most of the metallic clusters, so which have this FCC kind of crystal structure in their bulk form, so they will behave something like this. Okay, but if the uh, material is different with different atoms, so if it is non-metallic, it can be different. Okay,
Okay,
so
sir.
this is not, let's say, I would say, I mean, don't really like keep it in mind that yeah, this is the number which will decide whether the structure will be important, or the geometrical structure will be important, or the electronic structure will be important. But just remember, so these are the two things which can decide what will be the size of the particle. So the size can be also different. You can take different number of atoms. Okay, so you can take 1,000 atoms and you can create a cluster. You can take 1,001 number of atoms and you can also create a cluster. Okay, so it is not like that cluster may not exist. It may, but the question is which is more stable. That is all. Hmm?
Yes, sir. So, like now we have got to know that these are like some these are not strictly bound to a particular material or atom. So, this is for the specific element or atom. So, is there any general criteria to determine whether like it is the criteria whether that
No, it is one
smallest
has to do
particle
some. You have to do some calculation, theoretical calculations, and normally it is, as I said, this is still kind of an active field uh, in the research community. You know, when you want to know what is a stable configuration. Okay, so you have, let's say, we start with 10 number of atoms. So, what is the best way that they will be arranged so that the structure has a minimum energy? Okay, so that is always the basic idea. So, the atoms will be arranged in such a way, or the clusters will have a geometry or a shape which will always have a minimum energy. Okay, and for that, so you have to calculate. So it is, as I said, the best answer can be given by your quantum mechanics. Okay, so if you solve the Schrodinger equation, and then you can clearly say what will be the atomic positions which will lead to the minimum energy. But it is not so easy, so therefore you have to go for a lot of assumptions or approximations in calculating the structure. And there are different theoretical or models that exist which one can so basically all these problem boils down, or like if you want to put it in a simpler way, so how you can calculate the effective potential, this VR term in the Schrodinger equation. Okay, so if that potential you can define in a the best way, so then you basically get uh, the electronic structure, and you can describe the atomic position or the structure, and everything you can then define. Okay, so so the central problem always here is how you define this potential box or potential well. And so you always have to start with something which is easier. Okay, so you can take a spherical harmonic potential like shown in the left, or you can take like a box like potential where, so one thing is quite clear that here we can say these valence electrons or these electrons which are loosely bound, so you can assume them as the valence electrons which are kind of experiencing a effective or mean potential or an average potential due to all the nuclei. Okay, so nuclei, all the ions, let's say, so nuclei plus the electrons which completely fill the cell. Okay, so uh, so like what we saw in the example, so if you take sodium atom, so you have the ion you define by, you take the nucleus plus the 10 electrons, so which basically fulfill the the electronic cell. Okay, so that is your sodium plus ion, and then this one single electron is basically is the valence electron which will experience that potential due to the ion. So now when you arrange them, you put them together, so you now take 10 number of sodium atoms, so you make a cluster. So now how do you arrange them? So depending on the arrangement, so this potential well will be defined. Okay, and so then what is the best way to describe that potential well? So people observed that you can take a spherical potential well, or you can assume it's like a box like potential, but somehow it does not match with the experiment perfectly. So then uh, in this Galium model what we discussed yesterday, so basically then the model tells you that it is probably something in between, so it is not either spherical like a harmonic oscillator, or it is not perfectly like a square well, but it is something in between. Okay, so it's a mixture of that, and then with a where you have the bottom, here you have a like a rounded, it's not a sharp uh, corner you have, but kind of rounded corner you have, so it is like a mixture of this spherical this harmonic potential plus the square well potential. I mean, still this is an approximation which worked well for the sodium atom, let's say, but if you take aluminium or some other atom, so this may not be exactly the same potential uh, what is shown in the middle, so it can be different. Okay, so therefore the atoms will be arranged depending on, or this potential will be defined by the arrangement of atoms. Okay, and then consequently you get the electronic label and you fill it up and so on. But what is the structure and everything, it is not, again it is not easy to, so you can see the electronic structure by doing So you shine it with a UV light. Okay, so you look at the absorption spectra. So from that, you can calculate, or you can calculate the ionization potential and so on. So from that you can calculate the energy levels. Okay, but this structure, it's not easy to see it. Even under microscope it is not so easy. uh, and also another thing is they are sometimes not that stable, and therefore a lot of theoretical modeling that exists. And of course, as you know, theoretical modeling is always not accurate, so you have to have approximations and so on. And this is where all these models are developed, and people have observed all kinds of structures. Okay, so like core cell like structure or hollow structure, of all the different geometries that can exist in cluster. So it is, so if you are really interested, one has to go to which particular system you want to study, which cluster type. Okay, and then you carry on with the theoretical modeling of that. So, and in a simpler way, so first you have to approximate the proper potential. Okay, clear or?
Yes, sir, clear.
Okay. Yeah, there is also your question about this, why we have this 1s, 1p, like that, right? That was your question yesterday?
Yeah.
Yeah. So this is again due to something, it depends on what kind of potential we are talking about. Okay, so let's say, uh, let me go to the, yeah. Okay, so let's say we have a harmonic potential. So just I'll describe it briefly. So that means your potential is of this nature, okay, and the other potential is Coulomb potential. So which is happening in case of your atomic spectra. So here you have basically will be some constant pi, let's say. Okay. So this is, so this is a 1 by r potential. This is r square potential. I mean they are. So you can then calculate your or solve your Schrodinger equation in uh, using spherical polar coordinates. Okay, so r, theta, and phi, and but both will have different energy eigenvalues. So all those exercise, I think in physics, the students already have done these kind of exercises. So what is the energy eigenvalue for this harmonic oscillator or harmonic potential? Anyone?
N plus half h at omega.
Okay, so let me write it n or small n. Let me write n plus. So if I'm taking a three-dimensional one, so n plus half will be a one-dimensional oscillator. So if I take a three-dimensional one, so I can write it down as n plus 3 by 2 h cross omega. Okay, so this is the energy eigenvalue. So that means n will be equal to, so it can be 0, 1, 2, and so on, right? So energies will be accordingly 3 by 2 h cross omega, 5 by 2 h cross omega, and 7 by 2 h cross omega. So this is how, so if I take a potential like harmonic oscillator, so these are my energy levels. So n equal to 0, 1, 2, and so on, right? But when you solve the Schrodinger equation in spherical coordinates, so typically you get a different. So n is your quantum number, right? Uh, So rather, what we take in that, also again we get a radial quantum number and angular quantum number. In that case, you can write down your energy will be equal to 2nr plus L plus 3 by 2 h crust omega. So here nr is, yeah, they are again quantum numbers. Okay, so radial quantum number, because now you separate your wave function into a radial part and an angular part. So there will be your when this electron, you are studying the electrons energy levels, so you can, it can have a radial distribution as well as an angular distribution. And this angular distribution, basically you write it in terms of this spd. Okay, so this is the orbital what we talk about, and you also have a radial distribution as well. Now if you look at this uh, energy eigenvalues, so let's say if I say, and these are again integers. Okay, this nr and l all are integers basically. So here we can take any combination. So let's say we say the ground state is 3 by 2 h cross omega. So what will be the corresponding value of nr and l, which will give rise to this? So nr I take 0 and L will be equal to 0. So that is the only possibility. So I'll get a ground state, right? And let's say I have E1, which is the first excited state. So how do I get that? So I'll have NR equal to 0, right? And L is equal to 1. This is how I can get this 5 by 2 h cross omega, the second, the first excited state. So if I want to go to the second excited state, which is 7 by 2 h cross omega, so I can take nr is equal to 0, L equal to 1. I can also take now nr equal to 1 and L is equal to 0, right? So this is also will give to me 7 by 2 h cross omega. So now you see here, so there is no restriction on combination of nr, this quantum number nr and L. And this is typically, so you call it like 1s state. So this will call 1p state. Okay, so because this sp in nomenclature we get it from like what we described for atomic orbitals, electrons in atoms. So that is what we just keep. So L equal to 0 will be s, L equal to 1 will be p, and then the next one will be nr. So it could be 1 D, or it could be 2s. Okay, so this is how we get this combination of 1s, 1p, 1d. So you can also have for higher energy, so you can keep on doing that. So you can also have 1p, I mean 1f, 1g. Okay, so all these combinations are possible. So there is no restriction as such that this combination, so L has to be less than n, or has to be smaller than n. So this restriction actually comes in when you take this Coulomb potential, this 1 by R potential. So if you take your potential as is proportional to 1 by R, so which is your Coulomb potential. So in that case, your energy level is, so you take your ground state 1 divided by n square. So there is a minus sign, right? This is how, this is 1 by n square dependence. So you can, n will be equal to 1, 2, 3, and so on. So you can also write it down in this radial, so you solve it in spherical polar coordinates. You can also write down is, so here n will be equal to uh, nr, yes, nr plus l plus 1. So this is your n, value of your this integer n. Okay, 1 2 3 and so on. So now, so nr has to be like, will be equal to 0 or 0 1 2. So it's a positive integer. Okay, and if I write it down, this nr value will be n minus l minus 1, right? So this is a positive integer, which is always, let's say, greater than or equal to 0. So this tells you the condition that, now if you rearrange this equation, so what you have, n minus 1 will be greater than equal to l. So this is what, this condition which leads you to this existence of only one s. So you cannot have two, one p and one d, because of this restriction. And this is all due to this different potential what we have. Okay, and so here in this atomic orbital, so you'll have 1s, then 2s, and 2p. Okay, so then 3s, 3p, 3d, and so on. So you cannot have a 2d or a 1p or 1d, like that. So this restriction comes due to the this discretization in this of the energy levels, and basically it is due to the potential, which is a Coulomb like potential. Okay. Okay, so we will start. If any other question, others, if you have. Okay, so if not, uh, yeah. So yeah, here we have, like as I said, so you can have one S, one P, one D, and two S. They will be in the same. So you can have then one F, maybe two P, and so on. And this is therefore the magic numbers will be different here. Like we have two. So this is again like. So corresponding to each L, so the ml values will be from minus L to plus L, like as before. So for one L value, so you have the ml values will be from minus L to plus L through 0. So that means the p level will have three degenerate states. So px, py, pz, so 6 electrons. So now the magic number becomes 8. So 2, 8, then 20, and so. So d level will have like 10 electrons, right? And so on. So this is 12. So you'll get the magic number 20. Okay, so on. So therefore, this is the difference due to the this Coulomb, the potential, how the dependence of the potential on R. Okay, so let me start something different today. I mean, related to this, but a little bit something new, which is actually kind of actively being researched nowadays. These are known as this colloidal clusters. Okay, so what is colloidal? Colloidal means, so typically, let's say you take a cluster. Okay, so you can take a gold or silver. Okay, so one of these nanoclusters or nanoparticles, uh, and then you stabilize them in some way. Okay, so you put some ligands to it, or you stabilize by charges, so you can do that. And these are called, like you could call them as colloids. Okay, so it's again comes from, I think, some Latin or Greek uh, name, and that means it is like they are kind of these small particles, these nanoparticles or clusters are dispersed in in some kind of solvent. Okay. Oh, sorry. So they are dispersed in some kind of solvent, and this is what these colloids are. So the colloids are basically particles of a particular diameter, a dimension, okay, which are dispersed in a solvent. It can be a metallic, so it doesn't matter what is the nature. It can be metallic, non-metallic, insulating, or semiconducting, whatever. Okay. Uh, and what people are using it is so like if you want to make something out of these colloids, okay, so you have synthesized, so basically you synthesize them chemically, and then you want to use them for some applications. So it is not like you can take only one colloid or one nanoparticle and you do that. So you have to arrange them in uh, or like you have to put a lot of them on a device. Okay, so you cannot just, okay, you can take one cluster, okay, or one nanoparticle. So we will look at that maybe next couple of lectures. So how the electronic properties are very different if you take only single cluster or single particle or single quantum dot. But most of the devices like you want to make, you want to have like a large number of these clusters or colloids or let's say nanoparticles distributed over a substrate. Okay, so how do you do that? So one of the uh, typical or possible simplest way is known as self assembly. uh, So it is known as, oh yeah, I have written down already. So this is self assembly or self organization. Okay. So that means these clusters or the particles, they organize uh, in such a way and they form certain regular structures like what we see here. Okay, so they form very regular structures over large uh, scale, which is typically it can be of the order of a micron or even in millimeter order. Okay, so you take these small clusters, so which are few nanometer or maybe 50 or 100 nanometer, and then they self assemble or self organize into large structures like what we see here, like uh, and they give different shapes or different geometries. Now, on which factor that depends? It depends on, so in this case, what they have done is they have taken a cluster, yeah, this polystyrene beads. Okay, so they have taken polystyrene beads, which is it's like a polymer kind of thing. These are again spherical uh, particles or colloids which are 244 nanometer in diameter, so they are not actually that small, so still 244 nanometer. They are dispersed in water. Okay, so here this water is the solvent. And then so you put it on a substrate, so you can take like a silicon substrate for example, and you put a drop, so which has this lot of colloids here, and then you let it evaporate this water. But you have to so what they did is they evaporated it in a very controlled manner, very slow process, and then you observe this different structures. So you can observe a like a buckled structure. Okay, so here if I can I zoom in? No, sorry, it's now. So what you have is so different structures, like you can have a buckled structure like in A, you can have a perfect sphere you can make, but you can also make facets like you can make in case of a crystal. So you can make this icosahedral structure where you have different facets. Okay, so 100, 111, this facet you can also create. So almost you can take as this take these colloids, and these colloids when self-organized, so they behave almost like atoms, right? So like when you take atoms and you make a crystal, so you can make different shapes or different geometries out of that atom. So similarly you can call these colloids are kind of super atoms. Okay, and they form also crystals, like exactly like atoms, they form crystals. They have regular arrangement. So it can so depending on how fast or how slow this evaporation is. So here on the left side, what is mentioned is this evaporation rate. Okay, so this evaporation rate shows you that if the evaporation rate is slow, okay, so if it is slow, then you have this icosahedral structure, which is like almost like a crystal, that is you get. But then if you increase the evaporation rate, so if it is too high, so immediately the water evaporates. So then you get this complex buckled structure, because now the evaporation is not uniform, so it is happening. It is almost like when you form these crystals from a liquid state. Okay, so when you are forming the, so you have these atoms in the liquid state, right? And then you cool it down to get a solid. And in the process, if the process is too fast, okay, which is known as quenching, so you get a glass, right? It is like an irregular arrangement of atoms. So that means you get you don't get this crystalline kind of arrangement. So to get that, you have to cool it down very slowly. So it is similarly like here. So you take these clusters, and if you do a slow evaporation of water, so you get this formation of crystals, so which will have a clear long range ordering. But if you do it too fast, so then you get this irregular evaporation or buckled kind of state. So you can also create different structures, like crystal structures, and study these self-organization of this atom or colloids in a uh, extensive way. Okay, so this is one thing which is, I mean, this process of self assembly is quite well known for a long time. But nowadays people are exploiting for last couple of, or not couple, like last 1 decade or so. So people are really exploiting this self assembly or self organization to create larger devices uh, from these small nanoclusters or nanoparticles. Uh, I will share one review paper on this self assembly, with you, and then we will have a discussion on that sometime, let's say on uh, yeah, on Saturday we can have a discussion on that. So I will share a review paper. It is a little bit old, uh, but it is like, what are the forces which, so the actual question is, what are the forces which lead to this self organization or self assembly? So which forces are responsible that these atoms are arranged in a very specific way? Uh, I will share one uh, review paper with you, very nicely written. So I think it will be clear to everyone, all of you. So we can have a discussion on that on Saturday, because we have, I think, Saturday we have a